All right, so please have a look at the problem. Well, there's no statement here. Let me write the statement. So there's a rod OC, and this rod is rotating with the theta and its derivatives that are controlled. So theta dot, the angular velocity, theta double dot, that is the angular acceleration. For that instant, well, I should keep this line here. So for the instant we're talking about, theta equal to 20 degrees, this is what theta dot and theta double dot are. What we are expected to find is the forces that are applied by the rod OC. So when OC rotates, that is what is pushing the pin into the circular slot. If OC does not rotate, the pin stays stationary. So the rod OC will apply some normal force on the pin, and the pin, when it rotates, it requires some acceleration. So there could be a component, if there is any component towards the center, there could be a case that this channel could apply a normal reaction in any direction. We don't know that yet. So it could apply a normal reaction. So there is no friction, so friction can be neglected. So only normal forces can be applied by the circular channel and the rod. So this is one of those cases where the accelerations are given to us and we have to find the forces. Mostly we will have problems where the forces are given to us and we have to find the accelerations. But we do this a lot. So when we are designing mechanism, for example, to have an automated robotic system, then we will need a mechanism that should work in a certain way. It should rotate with a certain theta dot and theta double dot and so on for a given instant. So this information is the input, and the output is what kind of forces will be applied, so that we can design the material and so on for this case. If the force is, for example, the force we calculate is much larger than the force the pin can take the material, it might break. So we have to take those worst case scenarios. So please think about the problem, think about the approach. I'll suggest you write down what are the steps you would have taken to solve the problem. Don't solve it, but think about the procedure. Is there any clarification required in the problem? Are we clear about the problem? So let's discuss what steps we'll follow to solve the problem. Can I get some raise of hands, please? Yes. Direction of forces. Yeah. But so the answer that we have got is we'll find the direction of forces. But what does that mean? So force is what we have to find, both direction and magnitude. We'll have to find both, not just direction. So what is the first step here? Right, that's very good. So we'll find accelerations. Right. So acceleration, once you find, that is force divided by mass. Now for that acceleration, we'll have to choose a coordinate system first. So what are the possible choices of coordinate system here? Polar or NT? Yes, both are good ones. So normal tangential, I haven't discussed any problem in the class on normal tangential, but it's very similar to polar. So please have a look at the book, solved examples. So normal tangential is also good here. Now there are two choices of origin here. So we can choose the origin here as well. That's a good choice. It's a center of a circle, right? Is there anyone who does not agree for A to be our choice of center of circle if we are taking polar coordinates? No, we can, so the answer is we can choose O as the center and use NT coordinates, right, normal tangential. We can also use R and theta with O as a center. Remember, coordinate system is our choice. We just have to choose whichever is the most comfortable for us. And that comes with some experience. In this case, the possible choices, so we all agree that we'll not use Cartesian coordinate system. We'll use either polar or normal tangential. So let's choose polar. So for polar coordinate system, I have two choices of center. One is O, the other is A. You can choose any one. So let's choose O. That's more comfortable for me because O is the center around which the rotation is happening. The rods are rotating. It could be the case that A was much simpler. I don't know. So I'll ask you, we'll solve it using O as a center, but I'll ask you to try the same problem with A as the center. Polar only. So I'm trying to give you some sort of a recipe because problems can get quite complicated. So what happens is if we try to approach it in an ad hoc sense, somewhere in the middle we try to think of what will be the direction of acceleration here intuitively, it can be very confusing because we might get confused as to what our coordinate system is. So let's develop a recipe and then go step by step. But with experience, you will get more, things will get more intuitive. So you may approach the problem very quickly. In this case, the choice is polar with O as the center. So that means our R and theta, in fact, that is given in the problem, they become our R and theta. If we had chosen A as the center, then R would have been B, which is constant, so things could get much easier, and the theta or the angle would be this. But in this case, we have R and theta. What is the next step? Now that we have a coordinate system and we know theta, theta dot, theta double dot, we can go towards finding the acceleration. because what we have to find is the forces acting on pin B. So we have to write the equation, the force acting on pin B is equal to mass times acceleration of pin B. So we choose we find acceleration of B, and once you have the acceleration of B, we apply Newton's second law. On the point mass B, that is F vector sum of forces acting on B is mass times acceleration of B. So that will require me to draw a free body diagram. And we'll use components because vectors, so we'll deal with two independent coordinates, components. The acceleration of B, that is, we'll find AR and A theta components because we are working in polar coordinates. Now can we take half a minute to 1 minute and then try to find the acceleration of B? I want you to think. So what's happened in the quiz is I'm seeing that it was actually very subtle. If you had looked at the geometry, it was very subtle. Although the solution I gave you was very complicated because that uses polar approach, but you didn't really have to use polar approach. But the point is, this is, I'll stress on this, the JEE days are gone. So you will not be given a lot of experience with lots of problems, and the reason is because, see, I want you to think in the exam as well. You could practice 50 problems and be very good with that practice, and then go to the exam and get a problem which is one of those 50 problems. But we are not testing you remembering how to solve a problem. I really want to test how you think to approach a new problem. And believe me, I mean, ultimately that is what the aim of university experience is. For you, to make you, to enable you to be able to think about new problems. Because when you go to the real world after 5 or 10 years and you look at a problem, you will not remember anything. What you will have with you is that analytical approach to solve a new problem. And it is completely fine not to be able to solve a problem at the first go. So if many of you could not solve a very simple quiz problem, that is completely fine, because we are sort of unlearning that JEE approach where we had to solve many problems so that in the exam we can attack problems very effectively. But now the aim is to be able to think, and you can only do that if you try to think. I can give you a solution on the board, you can understand it really well and have a very nice day. But if I give you a problem the next day, you will not have enabled your neurons to be able to think. So please think about this problem for half a minute to 1 minute, and then we'll solve it. Try to do these two steps. read this comfortably? You can read this comfortably? So I'll move to the next page. Is there anyone who still wants to look at the figure? Okay. How many degrees of freedom do we have in this problem? Are they not two, r and theta? R and theta are linked to each other. If I rotate this thing with a particular theta from one theta to the other theta, do you agree that the r will change? I cannot independently control r and theta both. So there is only 1 degree of freedom. That's also important to know, because while we are solving things, we should know that r and theta will be linked. So I cannot represent r in terms of theta in the answer. So that's one more thing to note. You will have to, somewhere here in the acceleration, you'll also have to find the degrees of freedom. So once we find that degree of freedom is 1, then we'll have to find some sort of geometrical compatibility. If we get an answer of r in terms of theta and vice versa, then we'll have to find a relation between them. Since the number of degrees of freedom is 1, can we find r as a function of theta? It's an isosceles triangle, so we can write the geometrical relation. So now that we know r as a function of theta, we can differentiate it twice, because we will be needing r dot and r double dot in our acceleration expression. So this is purely coming from geometrical constraint for the given problem. It's not a general thing.
R double dot is wrong. Oh, sorry. Oh, yes, yes, yes. Sorry for that. Yeah.
Now it is correct. Thank you. Let me think. My brain's frozen now. So we have seen enough number of problems where theta dot was a constant. So this was a silly mistake I did. Right. So now that we have R dot and R double dot, all we need to do is to find AR. That is R double dot minus R theta dot square. So we will substitute R in terms of theta and its derivatives in terms of theta derivatives. So that's simple. Everything is in terms of theta and its derivatives. And the good thing is, in the problem that's given to us, theta and its derivatives are given to us for that instant. It's good. Everything should be in terms of theta. Similarly, A theta can also be found out because we have R and R dot in terms of theta, theta dot and theta double dot. So that's first step finished. That was kinematics. There was no kinetics yet, no force, nothing about forces.
Let's call this step number 1. This is step number 0, step number 1 and step number 2.
The next step now is to draw the free body diagram. Now what are the forces acting on B? So let's go to the actual figure. And remember, there's no friction. So what will be the direction of the force that is due to the rod OC on the pin B? Like this? Because the slot in the rod can only apply a normal force. Tangential is not allowed because we are neglecting friction here. I mean, the direction could be wrong. That's okay. We will get a negative answer. But
So let me call this R. That's the
force because of the rod R. Now what about the force because of the channel? Because the pin is also moving in the channel. So the slight movement of the pin can also result in the channel applying a force. Is this the force because of the channel? Channel can again not apply a tangential force because neglecting friction. We can complicate this further by asking you to have friction in the problem. But for now, we are not doing that. So this is our free body diagram. The two forces acting, one is because of the rod R, the other is because of the channel, which we'll call it the slot S. So these are two normal forces. I've also written r hat and theta hat because we want to find components of these forces along r hat and theta hat. So does the normal reaction have any component along r hat? I mean, sorry, did I write n? The r force, that's the rod force, does it have any component along r hat? Only the s force? So again you can see this is theta. That solves the problem. So our aim is to find r and theta, r and s, capital R and capital S, and we already know what fr and f theta are. Mass times ar and mass times a theta, and ar and a theta already are there in terms of theta. So everything can be written in terms of theta and its derivatives. They are known to you. You substitute the values, you get the values of forces r and s. Is that clear? What was A? Yes, yes, yes. Yes. That is what I wrote, right? The S, that's a force by the slot, is towards A. So this was A and this was O. Can I move on to the next problem? Now, towards the end of the last lecture, I asked you a question. Remember that tube problem? I had not drawn it very well, but I had put the picture from the book in that PDF that was on Moodle. I hope you had a look at that. So we will solve that problem again very quickly, but we'll talk about non-inertial systems. That's the idea of discussion in the second half today. So now I'm drawing it in a different way. what we are doing here is, what we did was we found out the tension T
because you have a string here.
that is either pulling the string or releasing the string with a controlled R dot. So that means R double dot was 0. That's how we are controlling the spool. So there were two cases. One was where we release the string so that the plug B moves outwards in the tube, and the second case was the plug B moves inwards towards the center of the tube. Now the whole thing, the tube was also rotating with omega. So in the top view that we are seeing here, we can see that theta and theta dot will be just derivative of theta, and this is R. So if we draw the free body diagram with the blue color, so there is one force, that is tension, that acts inwards, and there is another force which is normal reaction, which acts in the theta direction. Now this normal reaction force has a direction that depends on whether you are releasing the string or releasing the particle plug B, or you are pulling it back. So what we saw was the tension always acts inwards, that does not change, but F theta, or this normal reaction, is positive, that is it's in the direction that's drawn if you release the string. But if you pull the string, it acts in the opposite direction. That was solved using simple F equals ma in the polar coordinates, where the center was taken as O and R and theta were taken as shown in the figure. So that is where we had stopped. All right. Now my question was, the question to you was, what if you have a person who's sitting in the tube and measuring this? Although towards the end of the lecture I'll say that don't do this. Try to stay in inertial coordinate systems, otherwise your life becomes difficult. But we should have an understanding of inertial and non-inertial coordinate systems. So the person who's sitting inside the tube will also want to write the Newton's second law, although that person knows that the person is accelerating. So let us say that from outside, or the inertial frame of reference, the sum of true forces is equal to mass times the acceleration, and this acceleration is measured from an inertial frame of reference. The superscript inertial here means it is measured from an inertial frame of reference. Don't confuse it with the acceleration of inertial frame, because acceleration of inertial frame is 0. It is, the superscript means it is measured from an inertial frame. Now let's come to the person who's sitting inside the tube. This is not true, because forces are forces, true forces. So the person sitting inside the tube will have to add a fictitious force, which is not a true force, just to make sure that this equation works for them. So that's the idea of your pseudo forces or fictitious forces. So from this we will try to find what is this fictitious force. Okay, so this is what the fictitious force is. Now I'll want to understand what this difference means. So we'll draw linear situation. So you have an acceleration of an object, acceleration of an object, yes. So this time I am keeping subscripts. Subscript means it is off. So we have an object that is moving, and the acceleration of that object is measured as this. It is this, and that this is also equal to acceleration that is measured by an inertial frame. because an inertial frame will measure the acceleration of the object. Now we have a frame, another frame that is now accelerating. So that frame, since it is accelerating, will have its own acceleration. So again, subscript acceleration of the non-inertial frame. So this blue one is the acceleration of the object measured or with respect to the non-inertial frame. If the non-inertial frame was moving with the acceleration of the object, then you can see that the blue thing will become 0, because both will be accelerating at the same rate. So the non-inertial frame measures an acceleration, that's the blue one. And the inertial frame measures the acceleration of the object, the true acceleration. Is there any question? There are too many subscripts and superscripts here. If I take the difference between the blue vector and the object vector, what I get is the negative of the non-inertial frame's acceleration. So this is our fictitious force. You knew this from your understanding of centrifugal force or an accelerating frame. But we are formally writing this because now we'll have other kinds of pseudo forces as well, if you want to work in the non-inertial frame, although I'll recommend not to do that. So let's, well, let me give you a problem. You already have done this in the past. So you have a string and you have a mass. And this mass is rotating at a constant angular velocity omega. Now what you do is, you sit on the mass. Your frame is the frame that's moving or fixed to the mass. It's a 2D problem. Now you try to use the idea we have discussed here, and from that person, from you that is sitting on the mass, write the modified Newton's second law so that it works in your frame. All right? Now the second problem is, for the same situation, now what you do is, it's the same mass. You sit here. You don't want to sit on the mass. Halfway through. And now write the Newton's second law, of course, I mean the modified form with a fictitious force, because you really want to solve the problem from a non-inertial frame. And the third will be solve the tube problem sitting in the tube. Now you can choose where you want to sit, whichever is more comfortable. Because remember, non-inertial frame is our choice. Frames are always our choice. So you either want to sit on the particle or you want to sit in the tube. So you can decide how far away from the center you want to sit. You can always choose a frame that moves with the particle. And although you will see that sitting on the particle is going to be more comfortable in terms of using the ideas of non-inertial frames. But you try to do this yourself. I will put the answers to this in the slide for today, and then you can have a look at it. Now I want to discuss the feedback. There has been some very strong and critical feedback, so I'll open that feedback here and we'll discuss and see if we can make some changes to the way we are learning. Any questions here?